So as I stated at the end of the last video, our goal in this section is to try to understand how we could use Riemann sums to ultimately find the exact area under the curve of a function. So as I state here in this opening question, how might we possibly be able to do that? When it comes to Riemann sums, what do we need to do, or what do we need to modify in order to improve our approximation? And then, could we ever use a Riemann sum to obtain the actual value of the net area? Well, to kind of take a look at this, I'm going to take a look at this little applet that I have right here. You can see that I'm working with the function, and I'm trying to find the area under it from some point of A over to a point of B. For the sake of simplicity, I'm going to move this point of A over here to be right at the value of 0. So I'm trying to find the area from, say, 0 to 6 underneath this purple function. Now, I can see right now that I'm using 3 rectangles to try to do this. It looks like I'm using midpoint approximations. And I can see that, well, there's some area that I'm missing in white, and there's some area that I can clearly see that I'm over-grabbing, that I don't need, this excess area. So what would again be some ways that I might be able to improve my approximation? Well, there's lots of different ways that I might be able to attempt to improve it. Here are at least just a couple. Notice that what if I was to go ahead and adjust, say, if I was using midpoints or left endpoints or things like that. Like what if I used only left endpoints? Maybe that would help improve my approximation. Or maybe I use only right endpoints. Maybe I use something that's like 3/4 of the way through, right? I can kind of like adjust which point in my interval I'm going to go up from to hit the function. Maybe that's one thing I can kind of tweak or modify. Another thing could actually be, well, do all the rectangles actually have to be the same width? You know, I mean, we said that it was nicer to do that for our calculations, but actually, I don't necessarily need to have my rectangles be the same width. Maybe they're different widths. Like here, I have a middle-sized one, a really skinny one, a really large one, right? I could do all sorts of different sizes here, right? Just kind of changing them up, putting them in different positions. I could do a whole bunch of different things here. Okay, so that is another option that I could do. Or, of course, I could keep them all the same width. Doesn't really matter. The other things that I could change is, well, do I even need to use rectangles? Now, that's actually a topic that we'll get into more in a Calculus 2 class, where we'll talk about using other objects besides rectangles to estimate areas under curves. For the moment, we're going to put that suggestion on the table and wait to talk about that in a later class. But there's one other thing that we might be able to do to improve our approximation. And for some of you, you're probably already you're probably yelling it out. But it's, could I possibly just adjust the number of rectangles that I'm using? How about instead of using 3 rectangles, I use 4? Or instead of 4 rectangles, I use 10. Maybe by adjusting the number of rectangles, I could improve the approximation. Now, maybe all these different things work together, but there's something really interesting here. Take a look at what happens to the area under the curve and the approximation that I have if I continue to increase the number of rectangles that I'm using. Notice over here I'm up to 20 rectangles, now 25. So like, take a look here, I'm at 30 rectangles. Is this the exact area under the curve? Did I find it precisely? No, I mean, I can see the little gaps of white in there still, and I can see that I'm overshooting over here in a couple spots. So it's not perfect yet, but is it looking better? Oh yeah. Now, maybe I could just keep going, How many rectangles am I going to need before maybe this looks so good I can hardly see a difference? I mean, notice in here even, I can maybe see on the right edge I'm over a little bit, but over here I can barely see if there's anything that I'm missing, right? Notice now that as I continue to increase the number of rectangles, I'm up to 101. They're so skinny that I can almost just only see the black lines that divide the rectangles. In fact, if I keep going, notice I'm up to like 130 rectangles, I'm up to 160, I'm up to 200 something rectangles. I can almost only see like completely black lines now, right? Like they're so skinny in there that, wow, at 316 rectangles, it almost looks like I have the exact area. But if I was able to zoom in here, do you think 316 rectangles is like the magical number where all of a sudden I get the exact area? No. I'm probably still going to be overshooting a tiny bit and undershooting a little bit as well. But This is definitely way better than where we started. So how many rectangles do you think is enough? 300? 400? Maybe if I go to 1,000? Well, you might be thinking, wait a minute, what about if we kept going? What if we let the number of rectangles continue to increase? What if we brought back in the idea that calculus, remember, is all about? The idea of a limit. What if this number of rectangles up here didn't stop anywhere, but it just kept going off to infinity? Now what's interesting here is that I can see that actually, no matter whether I have an arbitrary partition or a uniform partition, that is, rectangles of equal widths or different widths, as I continue to go on and on, my approximation gets better. It actually doesn't matter as well, even if I was to have left endpoint approximations, I can still see that as I increase, my approximation gets better. If I had midpoint approximations, as I increase, my approximations get better. If I was to do right endpoint approximations, as I increase, my approximations get better. So the only variable here that really seems to matter is how many rectangles are we going to use. So how do we improve it? We can modify the number of rectangles that we use in our approximation. This is at least the most influential factor. We will let n approach infinity in order to try and obtain the actual area. This is our idea. So take a look down here at this definition. Suppose that I have a Riemann sum, and that's estimating the area, but so far it's only using n rectangles, maybe 5, maybe 50, maybe 5 million. Doesn't really matter how many. I know that the approximation still isn't perfect. Now, as long as this area lies between a continuous function and the x-axis, then notice what we're saying here. We define the area, the precise area, not the approximation, but the exact area to be the limit as n approaches infinity of our Riemann sum. So I can see here that as n increases, again, I'm increasing the number of rectangles that I'm using. Now, we are ultimately going to be able to see here that this definition doesn't require at all that we use right endpoints or left endpoints or midpoints or anything. For our purposes in this class, we will always be doing kind of right endpoints when we do these sorts of calculations by hand, and we'll see kind of how to do that right now as we look at example number 2. This is actually the exact same thing as what we saw in the opening example in example 1. Let A be the area of the region that lies under the graph of f of x equals x squared between 0 and 2. Now, I want to go ahead and using right endpoints, I want to find an expression for A that tells me exactly what A is, but as a limit. Well, notice this should be unbelievably simple. Notice that in the previous video, we already identified what the width was, how to find the right endpoints, and how to calculate the height in general for any of the rectangles we would ever use. And therefore, we could easily go ahead and almost use identically what we have here to answer example 2. The only difference is this example was built on the assumption that we were only going to use 4 rectangles. And so we're going to have to make a slight adjustment here to our height, and we'll see what other things this slowly changes. So let's take a look here. I know I'm going to need the 3 same things that we had back in example 1. I'm going to need to calculate the width of my rectangles, my right endpoints for my rectangles, and I'm also going to need to understand how to find the heights of my rectangles. So let's start again with our width, delta x. Now again, the width of my interval is still 2 down to 0, so 2 units long. But since I don't know at this time how many rectangles I'm going to use, I'm going to go ahead and state that I want to use n rectangles. So that way I can have n, the number of rectangles, move off to infinity. So my right endpoints are going to operate exactly the same way as they did previously. I can go ahead and say, starting from the value of a, I'm going to move over my widths of rectangles I times to get to the ith right endpoint. Again, if you need to, you can go ahead and think about what's happening over here in the picture. Right? We had a picture that looks something like this, and we saw that we had a value of 1/2, 1, 3/2, and 2. And so I had to move over 1 width for the first rectangle's right endpoint, I had to move over 2 widths for the next one, so on and so forth. So if I was to write this formula down more simply, notice this would be 0 plus, and my width here simplifies to 2 over n. So I would have 2 over n times I. So that would be my formula for the right endpoint of any given rectangle. Now, of course, to find the height, I know I'm supposed to compute f of xi star. So I would do my xi star, 2 over n, times I, all squared. And so now I have all of my different pieces, and so I can conclude that my area is exactly equal to, starting at rectangle 1 and going to rectangle n, I'm going to add up the areas of my rectangles. My area of my rectangle should be my height, which is given by this, times my width, which is given by this, and this would give me my area formula for n rectangles. But to get the exact area, I need to put a limit on this as n goes off to infinity. So this here is the formula that I would need to compute the exact area underneath this curve that goes from 0 over to 2. Notice that would be all of this space precisely. I can find all of that using this limit.